Okay, so our next session will be taken by Professor Anirudh Kulkarni. So welcome, sir. Welcome to the session. You can begin your session. Participants, let me just inform you that Professor Anirudh Kulkarni is our esteemed faculty partner. He's guiding one of our semester-long intern and also a summer fellowship student. So he has joined the team recently, and we are really thankful to him for this support.
Sure. Thank you very much. First of all, thank you, Palmem, and the entire FOSSEE team for giving me this opportunity to present my work about porous media. Okay, as I was saying, that I think the opportunity for this presentation, and also I hope that at the end of this small talk, uh, I you know bring your attention towards the porous media solver of OpenFOAM and how you can build your own porous media solver. The objective of this talk is threefold, in the sense that there are three objectives. The first objective is to bring attention to the existing solvers that are there in OpenFOAM for porous media. The second objective is to inform or guide you on how to modify that solver to meet the research requirements, and the third is to overall provide an impetus to the usage of OpenFOAM for porous media modeling. If we briefly talk about the overall history of porous media, porous media, by the way, I mean, my PhD thesis was on porous media. I had used porous media as a passive way of enhancing heat transfer in a flat plate solar collector, and that is how I have been introduced to the porous media field. So, if we talk about the history of porous media, it all started by the famous Darcy's law in 1856. I don't know if you know this, but in Lyon, France, Sir Darcy was uh, a civil engineer, and he was given the problem of designing the water filtration system for the city. And through that experience, he had developed this particular theory. Uh, I mean, almost 170 years of scientific development is what it led to this point that we are here today. It all started with his empirical observations that we are looking at the porous media theory. Later on, Forsheimer extended it in his 1901 works, and then Brinkman's viscous stress contribution of 1947 led to further development of this theory, and finally Ergen in 1952 put them all together and put it in a broader perspective. Later on, with Whittaker's volume averaging theory of 1967, and then Professor Waffai's interface boundary condition of 1981. Is all eventually it all led to the final porous media model that we have, that is the extended Darcy Brinkman Forsheimer model that we have or that we see today. Whenever you come across any research article who more or less talks about the macroscopic modeling of porous media, they more or less will end up using this article or this model. Obviously, as the numerical methods develop later on, and then OpenFOAM also, we could see some libraries built for that purpose. I will quickly walk you through, how it all went down. So, as I said that, this was, or Professor Darcy came up with this particular porous media experiment, and or porous media experimental setup, wherein basically it's a simple setup wherein you study flow through a porous material. So obviously, porous material has voids. These voids are interconnected, and it occurs resistance to the flow, and because of this, you see a pressure drop. So at the end of the day, what he came up with, it was a simple correlation for the flow rate and the pressure drop, and that is how he understood that there is supposed to be a resistance term which controls how easily or how difficult the flow is inside this porous medium, and later on this term was known as the permeability. So if the permeability value is high, that means that flow can easily flow through the porous medium, and if it is low, then obviously it means that the flow offers resistance to the entire overall flow. All right. Later on, if we talk about the Forshammer extension, so Philip Forshammer was an Australian hydraulic engineer. Again, he made a crucial observation that Darcy's model is very linear in nature, and it applies only for slow flows. In the sense that if the Reynolds number is very less, where inertial effects are not significant, only then the Darcy's law holds, and when the velocity or overall Reynolds number of the flow increases, this law doesn't capture the physics as it is. So he suggested inclusion of another term into this particular equation, which includes the inertial term, in the sense that we have now a quadratic velocity term. Although this work was published and later on it was recognized, and if you look at the modern form as we see it, you pick out any porous media research article, you will find these two source terms prevalent in the momentum equations. The first is the Darcy term, which includes the viscous resistance, and the second is the Forshammer term, which includes the inertial resistance. As you can see, inertial resistance, because we have the quadratic term of the velocity. This was the old form, and this was the new form, or rather, this is the new form that we, more or less model today, for macroscopic flows. And now the assumption that this particular model has is that it is, the porous medium that we are looking at is a packed bed of spheres, and that is why we are looking at this model, because in real life porous media is not a packed bed of sphere. Indeed, it has very tortuous paths, and there is more to it. Obviously, for a macroscopic flow, this may not be captured, so we limit the model to this form. All right. Then later on, what happened is we came to Brinkman's work, Professor Brinkman's work, where in 1947 was Brinkman. He made another crucial observation or contribution to this model, that near the boundaries between porous and clear fluid region, so where the porous media stops and the clear fluid region begins, the velocity gradient is quite steep, and the viscous stress effects become very important. This is what he observed, and this is actually very indeed very important, because when the flow enters the porous medium, there is a certain resistance that it faces, there is a certain change in its local velocity, and when the flow escapes the porous region and again re-enters the clear fluid region, there one sees a sudden jump in the properties, in the sense that now the resistance that it faces, it was facing earlier, was not there, and hence the velocity gradient was quite steep. Viscous stress effects became quite important, and thereafter he suggested that we should include indeed this term in the equation, which, as you can rightly observe, is nothing but the advection term from the Navier-Stokes equation. He suggested to include this because it was very important. Rather, the Laplacian term, as I should rightly point it. So the Laplacian term should be included in this model, so as to take into account, because as I would like to repeat it, that when the flow near the interface between porous medium and the clear fluid, we see unphysical velocity discontinuity, as he had referred it to, and hence it becomes very important that we also include this. And hence, again, if you open any paper on porous medium, more or less you will find the word extended Darcy-Brinkman-Forshammer model, and that is the reason. The reason is because of the inclusion of this Laplacian term in the model as well. Now, how does the later on developments fit into it? So in 1950s, Sabri his work was further again influential. He was a chemical engineer, and he developed correlations that connected the Darcy-Forshammer parameters to the medium's microstructure. Because so far, whatever discussion we are doing is more or less related to the macroscopic model, in the sense that we are talking about properties like permeability, and not talking about porosity, which refers to the amount of void that is there in the medium, the non-dimensional number, right? So he developed multiple correlations, and the famous Ergun equation, which is this equation over here, right? So that correlates very beautifully the macroscopic flow resistance to the microscopic parameters, that is porosity and the particle diameter. Because any experimentalist who is working with porous medium will, or in general, a person who has some knowledge about porous medium will ask about the particle diameter or the porosity. He gave a very nice correlation between them. The term this 150 and this 1.75, probably you may find some other numbers like 180 or other numbers elsewhere, but more or less the holistic model stays the same, and that is what it is, right? And how this is connected to the Darcy-Brinkman model? Very simple. In the Darcy model, the K, which is the permeability, and the CF, which is the force-chamber coefficient, they can be represented in terms of particle diameter and in terms of porosity. So usually what we do is, when we run simulations with K and CF, uh, and this is what I will come to later on in my presentation, the glaring mistake that some researchers do is they use the default model that is there in the OpenFOAM, which only talks about K and CF, and does not talk about porosity or particle diameter. But then again, if it is an external flow where the porous medium is in a very small quantity, then probably yes, inclusion of these parameters would not make changes to the overall results. However, if we are modeling internal flow, or even in an external flow case where the porous volume is sufficiently large, then yes, the porosity and the particle diameter will play an important role. I have presented these in my research articles. You may read it on later. And yes, this is indeed become important, and hence modifying the default OpenFOAM solvers for effective porous media modeling becomes very important. And we will talk about this. In fact, even for a lot of applications, there is still debate as to include whether this term or not. Because in many of the applications, it's not necessary. Even with Darcy numbers, we get sufficiently good results. And this discussion is still going on. It's not a dead end. It's still a very a relatively newer model, and is yet to being explored. Later on, I'll also present that how it may be also wrong. Anyway, so as I was mentioning about its connection, so the Ergun equation is related to the Darcy-Forshaman model in this way, and this particular expression particularly is very interesting because also known as the common Coulson variation, because this expression gives a very nice relation between the permeability and the porosity, and hence, or rather, why is this important? Because usually we may use permeability values like 10 to the minus 2, 10 to the minus 3 Darcy number values, the non-dimensional permeability, which is dA, the Darcy number is equal to K by h square, with h being the characteristic height. Now, it may so happen that we may use Darcy number values of 10 to the minus 2, 10 to the minus 1, and we may use porosity values like 0.6, 0.5, which isn't realistic, because for achieving that level of permeability, you need to have a certain minimum porosity value. And this relation very beautifully gives that to us, meaning I may have zero permeability with one porosity. If all those voids which are interconnected does not appear out on the surface, the medium may still be impermeable, but may have very high porosity value. So it's very important for us to have the right porosity and permeability combination, and the carbon Coulson relation very beautifully gives that to us. All right. So that's what is the importance of a gun relation. Then let's talk about the volume averaging theory. So Stephen Whittaker, obviously his contribution to this entire porous medium journey lies in the volume averaging theory, which was very popular in 1960s and beyond. So this is purely a rigorous mathematical framework, in the sense that it connects the pore scale physics to continuum scale equations. So the volume averaging states the theorem. This relates to the average of a gradient to the average of a average plus surface integrals. That is what is important, and this framework is completely fundamental. It tells us exactly how to derive microscopic equations from microscopic physics, provides closure relations for unknown terms, and establishes the conditions under which continuum models are valid. So again, it becomes very important for this entire porous media discussion. But then there was again Professor Wafai's contribution in the sense that Professor Wafai, yeah. So as I was saying, Professor Wafai is interface boundary condition. That is again that holds a significant contribution to the overall porous media modeling in the sense that how to effectively or properly model the clear porous and clear fluid region, or the couple how to couple the porous and clear fluid region that they had provided, and that is again very important and pertinent to this particular discussion. Now, if we talk about the overall the concepts of porous medium, let us talk about a few fundamental properties. What is porosity? Porosity, as I said, basically it gives us the overall idea of how much of the medium is void and how much how much of the total medium is void. So for instance, if you have porosity zero point 0.1, that means it's not so porous, and if it is zero point 0.9, it's very porous in the sense that the voids overall are in higher number or is in higher number, and occupies most of the medium. That is what it shows. That is the what is porosity. And permeability, as I already mentioned, it sort of gives us an idea of how easily the flow can the flow can with tortuosity and all those things. But then again, those things are not pertinent to our discussion because more or less these two quantities are sufficient for understanding. All right. So representative elementary value of volume, or also known as REV, it's again a very crucial concept. It sort of shows like what is the minimum volume over which we can define some meaningful results, wherein we don't have to take the entire medium, or we also can make sufficient correlations between the pore and the pore scale and the macroscopic results. So it's sort of like a play between them. So for scaling, yes, it's very important approach. And then again, this is another important point: Reynolds number. Reynolds number, based on the flow regime, obviously you will have to take into account what particular formula to use, because see, it all depends on the kind of model that you are using, right? So we may have one Reynolds number for the macroscopic flows, one Reynolds number definition for, say, the particle-based diameter, one Reynolds number based on the permeability. So it all depends on which Reynolds number or formula that you are going to stick to. It's very important that you take into account the presence of the porous medium and then calculate the Reynolds number. Say you are modeling mixed convection or you're modeling natural convection, meaning you're taking into the consideration of pi and z, then yes, we're calculating the Rayleigh number, the Richardson number. You should take into account the presence of porous medium. Say you're modeling the mass transfer, then Sherwood number. Yes, you'll have to take into account the presence of porous medium. This is again another mistake which researchers do. They take the macroscopic constants, which is incorrect, and we should take the constants along with the presence of porous media terms. So if suppose we talk specifically about the complete Darcy-Brinkman-Forshammer model, in the sense the extended Darcy-Brinkman-Forshammer model, these are the Bernoulli equations generally when we model, wherein as you can see, we actively introduce the epsilon or the porosity term along wherever there is any local variation of velocity. So in the momentum equation, you will find that. In energy equation, you should find that the presence of this term, and then of course there is the source term, the inertial source term, the viscous source term. Yes, they will be there, and based on that, you can do accordingly the scaling and the non-dimensionalization. These are the parameters for that. This is another example of a non-dimensional momentum equation based on the porous medium theory. I hope up until this point we are comfortable in the sense of the sort of the discussion that I've made overall on the porous media modeling technique. I will like to take a minute here and open the discussion for, the open forum for a discussion. If you have any doubts, you may ask, so that we can then move ahead to the open foam solver modification. Please let me know if you have any doubts so far. Okay, in that case, we can move ahead. All right. So, what about boundary conditions? Yes. So, at the walls, obviously, if suppose there's no slip, we'll have no slip. But then at the porous fluid interface, we need to ensure the continuity of velocity, the continuity of normal stress. We may also include these conditions, or say the Whittaker or OT conditions accordingly, depending on the case. But yes, this is very important. Another common mistake which researchers do when they write their own code, in-house code, or even say are working with OpenFOAM, it's very important that we take into consideration the interfacial treatment, and one needs to take an appropriate model for that. All right. So, how to, or these are the relations for further calculating the permeability to microstructure for, say, practical applications and so on. Again, we have talked about this before. So, let us directly go now to the OpenFOAM implementation. So, now in OpenFOAM implementation, these changes probably we will have to make in the sense that the discretization and the pressure correction there as well will have to include the local porosity term. I think I should now stop with the presentation and directly share the screen and show you the solver so that we can have that discussion. So let me. So here is the solver. I mean, I've taken the liberty to write a very abridged solver. So that I can explain it very easily. Let us, okay, let me directly go to the solver. Yes. So, all right. So we will have the usual things, and this particular inclusion of the header file would be there to take into account, existing the porous media library that is there in the OpenFOAM. Other things are there as usual. Now here, what I've done is that the create fields I've optimized a little for performance, and I pre-declare a couple of things for convenience. So we would need two additional, statics. One is porous index, and another is porosity. Why? Because for a general finite volume solver of OpenFOAM, it will not be able to identify, or rather, we should create a mechanism. Let me put it this way: we should create a mechanism for it to identify the porous region and the clear fluid region, and then assign the porosity value or the porous properties to it. So, what we will do is we will include a porosity index, which will be zero everywhere by default, which will indicate a clear fluid region, and then whenever we come across the porous zone that we will create by using toposet and set fields, uh, that will, in that region, we will set this porosity index as 1, and then it will identify that particular zone as a porous zone, and then accordingly, we can assign it those set values. Other things are as usual. We'll have the pressure field, we'll have the velocity field, and the other things are there as usual. From the create fields, we'll have a laminar. I mean, I have created a simple laminar case for a Newtonian fluid, so you'll have these things, nothing fancy. But yes, here, this is new. All right, this is new in the sense that, as I said, we'll create this field, and we will, during the runtime, we will read it, and but obviously we'll not write it, but we'll read it because this is important, so that we can make sure that each time the pros rule is there, and then we can assign or keep assigning the property to it. All right, this is the modified portion. The concept is very simple actually. The idea is that once the solver identifies it's either 0 or 1, the porosity index, then accordingly we can give the porosity value to it, and based on the porosity value, then again the solver may assign the corresponding properties from the constant folder, or the constant folder, that's a particular file. I will also show that now. So yeah, other things are as usual. This entire thing is modified. The idea is, as I've told you, it will look up and it will assign. Simple. All right. Yeah. So this is a simple, the pimple loop, simply the pimple loop. And here is the another modification, in the sense that now whatever porosity value we fetch from the solver, it should be also included in the Goan equation. Meaning, if say we have dou T by dou U, this U, the macroscopic velocity when it enters the porous medium, it should be divided by the local porosity. So we'll have U by epsilon. Similarly, in the divergence term, we will have U dou U by dou x. So in that, we'll have U by E, dou U by dou x divided by or into 1 by E. So overall, it becomes 1 by epsilon square, and that should be reflected here by through this term. The same applies to the Laplacian term. Likewise, it should also be included in the pressure correction as well, and that has been done. So that we can get overall the local velocity variation effect, and other things are again the same. Uh, I mean, not much to show there or discuss there. So once we compile this code, I have created a simple cases. Let me demonstrate one case to you. Say of the impermeable case. This is a completely, I mean, the cylinder is completely impermeable. So in zero, we'll have the regular P and Q. And apart from that, we'll have porosity and porosity index as discussed. So by default, if you see, porosity is 1 everywhere. That indicates the clear fluid region. And porosity index is 0 everywhere. That indicates the clear fluid region. And when we run the block mesh and topos dict and set fields dict, it's 0 everywhere, but then at some points it is 1 or it becomes 1. That indicates the porous region. All right. And similar thing happens to the porosity. All right. So this is what is happening in 0. Let me directly go to the constant. Right. In constant, again, transfer property, yes, as usual, nothing fancy happening there. We need these three files. The first is where we will, yeah. So here is where we will be doing the changes as is required, right? You may define the Darcy number, Reynolds number, porosity value, depending on your requirement. And again, this porosity value and the Darcy number, this values you can get from the carbon cogency relation, which has been mentioned here. The Forshammer term, the D and the F, how they are calculated, and the carbon cogency relation. By using that, you can update these values so that it becomes easy for you. And these value then will be, included ultimately here via this file. And this is what is interesting. What will happen is based on whatever values you have mentioned here in porosity dict, these will be automatically calculated. For that, I have written a simple Python script, which is this. So if you run this Python script, automatically this file will be updated with the values, and this script has the carbon cogency relation inbuilt into it. Obviously, this is an overkill. You can do it manually as well, but yes, it beautifully automates the things so that every parameter or all the parameters can be calculated immediately and can be placed accordingly. So, for instance, this velocity I can go and place in G based on the Reynolds number, and yes, these things can be done. But then again, it's up to you. You can do it manually as well. But yes, we would be requiring these three files additionally. And then in system, here literally nothing has to be done, in the sense that only block mesh has to be modified for modeling the maybe cylinder case or cavity case, whatever you want to model. Currently, I will demonstrate a simple flow across a square bluff body. So let me quickly open para view and show it to you. All right, so I have run for Reynolds number 100. Obviously, this is not precise, but this is what it is. So this is for Darcy number 10 to minus 6, which means it's a completely solid cylinder. That means the flow should not enter the cylinder. Obviously, that does not happen. The flow will enter. However, it will not leave the cylinder. It will simply get blocked, and that means it's a completely solid cylinder. So, beautiful physics right there. So let me just pause it right here and show you the streamlines. So just to quickly show you, as you can see, the streamlines The streamlines, they are entering at some points, but they are not leaving the cylinder. They are just being here just for the sake of continuity are being calculated. These this doesn't make sense. Then there is a wake that is there, and that's that. So that's in number 10 to minus 6, and the CLCD oscillation would look something like this. Pretty simple, straightforward. Let us then talk about 10 raised to minus 4. So in the case of 10 to minus 4, now what changes do I can I do here? First thing, you go to constant porosity properties. Oh my bad, porosity dict. In porosity dict, you change it to 10 to minus 4. Run the Python script. Automatically, all these values are entered. As you can see, these values are very much different than these values. The D and F value has been changed. Right? So how is this different from the conventional OpenFOAM solver? Very simple. In the conventional OpenFOAM solver, D and F, are they there? Yes. But what is not there is the inclusion of porosity. In the governing equation, in the overall code, it's not there. So that seamlessly comes yes. And then the interfacial treatment, yes. So that continuity comes very nicely in this particular solver, and that is how you can do it. Or okay, leave aside for the default OpenFOAM model for a minute. This is how you can build your own OpenFOAM solver for the porous medium. That is what you can take it away from this particular code. Now, for 10 minus 4, this is what we'll do. We'll modify the DASI number, we'll run the Python solver, and then these values will be updated, and we will simply run this case. And if I can show you, now, if you notice, DASI number 10 to minus 6 and 10 to minus 4, the flow pattern, they're almost same, not much or not many differences there, to be honest, because they are almost similar in the sense they offer very high resistance to the flow, so the flow almost not enters the cylinder. Let me quickly plot the streamline and show you. So here, as you can see, there, in comparison to the Racing 10 to minus 6, yes, there are more streamlines that are entering inside and leaving the cylinder, but not from the behind, from the side, and showing still there is some resistance that is being offered to the flow. Mostly these streamlines will be limited to this region and not leave from behind. That means that it shows still quite enough resistance to the flow. Then if we talk about it again, the CLCD pattern, we can see changes in that as well, right, in the values and all those things. Let us then talk about 10 minus 3. Again, the same drill, change the values, run the Python script, the values will be updated, right? Directly run the Python for now, and here you will start to see something very interesting. Now you see in the cylinder, the flow has started to enter, and hence the physics also has now changed significantly. So the wake pattern is also a little different in comparison to number 6. So let me quickly show you the streamline patterns. Now, as you can see, in comparison to 10 to minus 6 and 10 to minus 4, a significant amount of wake enters and leaves the cylinder, and therefore, obviously, there will be change in physics. And let us go to 10 to minus 2 and 10 to minus 3. You will see this is how the CLCD pattern will be. Now let us talk about 10 to minus 2. Obviously, 10 to minus 2. as you can predict, 10 minus 2 is the highest or very high, permeability value in comparison to 10 minus 6. So much so that now what will happen is all of the flow would have entered and left the cylinder all with almost no resistance to the flow whatsoever, and you would see no wake pattern behind. No vertex sharing behind, and this is how the streamline would look. You can see there is some resistance. The flow is still bending a little. There is some resistance. It's not like there is no resistance at all, but this is quasi through flow condition kind of a thing that you can see here. And this is quite evident from the CLCD patterns. All right. So to sum it up, if you want to build your own OpenFOAM solver for a porous media flow, you'll have to take into consideration not only the extended R-sibling Shammard model, but also the local velocity variation. Probably this was an external flow case. So you may not see much difference if you remove and keep porosity values. But yes, if you talk about internal flow or even external flow where the porous media presence is significant, then yes, you will start to see this difference or changes in your solver. So it's very important that we take into account the state of the art models and implement them, and how to implement them that I have shown you. So please let me know if you have any doubt in this entire discussion. I had planned to complete in around 35 to 40 minutes, and I think I have done well. So please let me know if you have any doubt. I have kept very more room for the discussion, and that's the reason why I have the OpenFOAM code and solver right in front of me. So please let me know if you have any doubt. Thank you.
So I have one doubt. So you have assumed this cylinder as a porous.
Yes.
Yes. And sir, have you tested this for suppose in a whole domain we have multiple cylinders.
Okay.
That like in a reality, like I want to do we don't have spherical cylinders. We will have irregular shaped solid grains.
Okay.
So have you tested for such scenario? Like because generally then we will have like convergence issue, I guess.
Not really, actually. It will work fine. It will work fine for the description that you are giving me. It should work fine.
Okay.
Yeah, sure, sure. Thank you. I have worked on, with this solver, I have worked on both internal and external flow. Actually, an extended version of this solver I have included variable porosity, random porosity, and a channeling effect, and a few other things related to porous medium. But yes, this is a simplified version, but yes, it works fine. With OpenFOAM, you can write a very stable solver. This is what I can tell
Actually,
you.
why I'm asking because I'm working in the solute transport in porous media. So
Great.
generally we kept the laminar number less than 1 or less than 0.1.
Okay.
So, but when we have velocities and when we try to couple, so I have seen even the softwares like console, we used to struggle to get the concentration values.
All
Generally,
right.
we get a concentration more than the one, even if we are giving inlet boundary as one concentration.
Should
Yes,
work, I guess. If you have any or you are facing any issues, you can get in touch later on through LinkedIn or other social media
yes,
networks,
yes,
and
yes,
then you can take it up from there.
yes. Thank you.
Okay. Yeah. Yeah. Can I attach files in chat? I don't think so. That have option. Okay, I think there are some doubts. Okay, can we model solid gas interaction with porous media particles? For example, in packed bed reactors, yes, of course you can. But I don't think that for the solid gas reaction, a macroscopic approach would work. I guess it should work, but then I don't think that the accuracy that you are looking for, you would get. Packed bed reactor is a very common application of the macroscopic model, but then again, I'm not sure about how accurate it would be for that case. At least in its present form, it would not be. You'll have to take into consideration the other advanced models for that. And then Himanshu asks that in the flat-plate solar collector work, what assumptions you made for inducing the flow? Well, of course, it was a very simple application. Professor Saiduddin is a well-known personality in the renewable energy field. Based on one of his experimental work, I devised my numerical scheme or code. The idea is very simple. It's a rectangular flat plate collector. The top plate is glass, then there are two layers of further 2 layers of glass, then there is vacuum, then there is a copper plate. At the bottom, we have a very thick insulation layer, and in that, I had inserted porous medium for performance improvement. And through boundary conditions, I had simply given a simple code flow kind of a situation, so it worked that way. Again, the values were based on experiments. What I've done is I have uploaded it to my OneDrive just now, and I'll quickly share the link in the chat so that they can download it from here as well, whoever are interested. On purpose, I had kept the discussion very, succinct. I was hoping for more questions, but I guess now they are all tired from all the long sessions that I have going on. So I think I will not have more questions. Fair enough. If there are no more questions or discussion to be made, I think I can stop here. Thank you, again, to the panel for this opportunity, and looking forward to more. Thank you.